is less than or equal to 1 upon k square. Now, in the equality, if we want 2 here, then choose the value of k such that it becomes 2. Means taking k is equal to root 2, we get probability that mod x minus 2 is greater than or equal to 2 is less than or equal to 1 upon 4. Sorry, 1 upon 2. So probability of this event is always less than or equal to 0.5. So this way we got upper bound of probability of this particular event using Chebychev inequality. Now if we want to find exact value of this probability, suppose, then probability that mod x minus 2 is greater than or equal to 2 means 1 minus probability that x minus 2 is less than 2. So this is 1 minus probability that this is minus 2 less than x minus 2 is less than 2. So 1 minus 0 is less than x less than 4 means 1 minus, this is probability that x is equal to 1. X is lying between 0 and 4. It takes only integral values and therefore x can take 3 values 1, 2, 3 into plus probability that x is equal to 2 plus probability that x is equal to 3. So 1 minus this value is x is equal to 1 means 2 raised to minus 1. Probability that x is equal to, this is px means probability that x is equal to x. Same thing. So this is 2 raised to minus 2 plus 2 raised to minus 3. So 2 raised to minus 3 means 1 upon 8, 8 LCM. So here 4 plus 2 plus 1. So 1 minus 7 by 8 means 1 by 8. So the exact value is 1 by 8. The upper bound obtained by this is 0.5. So this way we can find exact value of the probability of some particular event. Similarly, even if we don't want to use the exact form, then also by Chebychev inequality we can find. Okay. Then let us take another example. Suppose x is a continuous random variable with PDF. Say fx is equal to e raised to minus x, x raised to lambda upon lambda factorial, where x is greater than 0 and 0 otherwise lambda is positive. Now actually it seems like the probability function of Poisson distribution. Actually if you interchange x and lambda, then it is e raised to minus lambda, lambda raised to x upon x factorial. So actually this is the form of Poisson distribution, whereas this is the form of gamma distribution, because here x is a continuous variable. X can take value from 0 to infinity. Here in Poisson distribution it takes value 0, 1, 2 and so on. So that is the main difference. Here we are given continuous, x is a continuous random variable and its PDF. So actually lambda factorial means gamma lambda plus 1. So I can write this as e raised to minus x, x raised to lambda plus 1 minus 1 upon lambda plus 1 factorial, x is greater than 0. So this way we can say that the distribution of x is gamma with parameter lambda plus 1. It is a continuous variable. Its PDF is gamma with parameter lambda plus 1.
lambda factor laki na kone gamma laki ka niche
lambda plus 1 gamma
Gamma.
factorial fx.
Sorry, gamma lambda plus. Now and 0 otherwise, that we know. Now if x follows gamma with parameter p, then we know that expected value of x is p. Variance of x is also p. For Poisson distribution, mean and variance are equal. For gamma with one parameter, also mean and variance are equal. So here in this case, if we call it mu, expected x, so that becomes lambda plus 1. sigma square variance of x, that is also lambda plus 1. Now suppose we want to find probability that 0 is less than x is less than 2 into lambda plus 1. Prove that this is greater than or equal, less than or equal to something. This we have to prove. Now let us apply Chebychev's inequality. So here by Chebychev's inequality, probability that x minus mu is less than k sigma is less than or equal to 1 minus 1 upon k square. Therefore, probability that mu minus k sigma is less than x is less than mu plus k sigma is less than or equal to 1 minus 1 upon k square. Now, if you further simplify, mu means lambda plus 1, k into sigma means root lambda plus 1. So lambda plus 1 plus k into root lambda plus 1 is less than or equal to 1 minus 1 upon k square. Now, if you want to get 0 here, we require probability of this particular event. So these two must be equal. So k is any positive constant that we know. So let us take k is equal to root lambda plus 1. Then this will be 0. So taking k is equal to root lambda plus 1, it becomes 0 is less than x, less than root lambda plus 1, root lambda means lambda plus 1 and one more time. So ultimately it becomes 2 times lambda plus 1 is less than or equal to 1 minus 1 upon k square means lambda plus 1, which is equal to lambda upon lambda plus 1. So this way, for this type of continuous variable also, we can get probability upper bound of this particular event. Now, this is about the Chebychev's inequality. Now, let us take weak law of large numbers. Weak law of large numbers. Let xn be a sequence of mutually independent random variables such that expected value of xn is equal to say mu n exists, means it is a finite quantity. Say bn is equal to variance of x1 plus x2 plus xn exists. Then, and if limit n tends to infinity, bn upon n square is equal to 0, means bn upon n square tends to 0, then for positive constants epsilon and eta so exist such that probability that mod x1 plus x2 plus xn by n minus mu1 plus mu2 plus mu n by n is less than epsilon is greater than 1 minus eta, and this is true for all n greater than or equal to n0, where n0 is some positive integer. So after certain number of terms, probability of this is less than epsilon, is this type of probability is always greater than 1 minus eta, where epsilon and eta are very small quantities. So this is the main statement of weak law of large numbers. We don't go into the proof of this weak law of large numbers. But when can we apply this weak law of large numbers? That is the main problem. So first of all, see expected. So there are three conditions. First condition, that expected value of each xk should exist, means it should be a finite quantity, which is mu k here, or you may write xn also. Then bn means variance of x1 plus x2 plus xn should also exist. So that is also a finite quantity. And third condition, that limit n tends to infinity bn upon n square or bn upon n square should tend to 0 as n tends to infinity. So these are the three main conditions. If these three conditions are satisfied, then we can say that weak law of large numbers can be applied. So let us take one example. Here let xn be any sequence such that they all are IID and independently and identically distributed. So expected value of xn is mu for all n. Variance of xn is sigma square for all n, and they are mutually independent. All xi's are mutually independent. Now we want to test. Suppose Sn is a partial sum, say x1 plus x2 plus xn, sum of first n variables x1, x2, xn. Now we want to find whether this weak law of large numbers can be applied to sequence Sn or not. That we want to test. So first of all, see, let us find Bn. Bn means here we have to apply weak law of large numbers for sequence Sn. So variance of S1, Bn is variance of x1 plus x2 plus xn. Instead of that, here S1 plus S2 plus Sn is equal to variance of S1 means x1, S2 means x1 plus x2, and Sn means x1 plus x2 plus xn. So this is equal to variance of, see, x1 is n times, so n times x1 plus x2 will be n minus 1 times, except in the first bracket everywhere x2 is there, so it appears n minus 1 time, n minus 1 times x2 plus etc. xn will be only 1 time in the last one. Now this is equal to n square variance of x1 plus n minus 1 square variance of x2 up to variance of xn. Remember that variance of x1, variance of x2 all are same as sigma square, that is given. So it is n square plus n minus 1 square plus 1 square, we can say, into sigma square, and sum of first n integers, natural numbers, sum of squares of first n natural number is n plus 1, 2n plus 1 by 6 upon sigma square. Now if we want to find limit of this bn upon n square, which is one of the conditions for applying WLL, so divide by n square, so it becomes n plus 1, 2n plus 1 by n sigma square by 6 is equal to, and as n tends to infinity, here if we divide by n, then 1 plus 1 upon n, which is exactly 1 as n tends to infinity, but here n is there and therefore it becomes infinity. So this way limit or bn upon n square does not tend to 0 as n tends to infinity, and therefore we cannot apply weak law of large numbers. Similarly, we can take some illustrations where all the three conditions may be satisfied and therefore WLL can be applied. So હવે પછીનું જે છે એ સેન્ટ્રલ લિમિટ થિયરમ વગેરે એ ડોક્ટર હેમિલ્ટન સાહેબ લેશે.
મિત્રો, હમણાં આપણને ગોઠી સાહેબે વાત કરી વીક લો ઓફ લાર્જ નંબરની, એમાં જે બે કન્ડિશન બતાડી કે એક્સપેક્ટેશન xi એક્ઝિસ્ટ થવું જોઈએ, વેરિયન્સ ઓફ સમ ઓફ xi એક્ઝિસ્ટ થવું જોઈએ, અને લિમિટ n ટેન્ડ્સ ટુ ઇન્ફિનિટી bn અપોન n સ્ક્વેર ટેન્ડ્સ ટુ 0 થવું જોઈએ. આ જે 3 કન્ડિશન્સ છે એમાં વીક લો ઓફ લાર્જ નંબર લગાડવું હોય તો ફક્ત પહેલી કન્ડિશન જ નેસેસરી કન્ડિશન છે, એક્સપેક્ટેશન xi એ એક્ઝિસ્ટ હોવું જોઈએ. જો પહેલાં તો આ કન્ડિશન સેટિસ્ફાઈડ થઈ જાય તો વી કેન એપ્લાય વીક લો ઓફ લાર્જ નંબર. પણ જે ત્રીજી કન્ડિશન છે લિમિટ n ટેન્ડ્સ ટુ ઇન્ફિનિટી bn અપોન n સ્ક્વેર ઇક્વલ ટુ 0 એ સફિશિયન્ટ નથી, એ નેસેસરી નથી. દેટ ઇઝ ધી સફિશિયન્ટ કન્ડિશન. પણ જ્યારે વેરિયેબલ્સ છે એ યુનિફોર્મલી બાઉન્ડેડ હોય, ઓલ xi's આર યુનિફોર્મલી બાઉન્ડેડ, ધેન ધી થર્ડ કન્ડિશન લિમિટ n ટેન્ડ્સ ટુ ઇન્ફિનિટી ઇટ બીકમ્સ ઓલ્સો નેસેસરી. એટલે પહેલી ને ત્રીજી કન્ડિશન બંને નેસેસરી ને સફિશિયન્ટ બની જાય છે. ક્યારે? કે જ્યારે વેરિયેબલ્સ આર યુનિફોર્મલી બાઉન્ડેડ હોય તો. બીજું, વેરિયેબલ્સ આર ઇન્ડિપેન્ડન્ટ એન્ડ આઇડેન્ટિકલી ડિસ્ટ્રીબ્યુટેડ હોય ત્યારે આપણે એક્સપેક્ટેશન xi એક્ઝિસ્ટ થવું જોઈએ. એક જ જરૂરી કન્ડિશન છે આપણી પાસે, અને એ જો લગાડીએ તો એ વખતે જે આ ફોર્મ છે એ આપણું જે વીક લો ઓફ લાર્જ નંબરનું એને કિન્ચિન્સ વીક લો ઓફ લાર્જ નંબર કહેવામાં આવે છે, કે એમાં જેમાં વેરિયેબલ્સ આઇડેન્ટિકલી ડિસ્ટ્રીબ્યુટેડ છે, દરેકના મીન સેમ છે, વેરિયન્સ સેમ છે. હવે એક્સાઇઝ જો આમાં અનકોરિલેટેડ હોય તો વીક લો ઓફ લાર્જ નંબર ઇઝ બીકમ્સ નોન એઝ ધી Chebychev's વીક લો ઓફ લાર્જ નંબર્સ. એટલે જુદા જુદા ફોર્મેટ માટે જુદા જુદા વેરિયેબલ્સ કેવા છે, અનકોરિલેટેડ છે, કોરિલેટેડ છે, ઇન્ડિપેન્ડન્ટ છે, આઇડેન્ટિકલ છે, એ પ્રમાણે આપણને જુદા જુદા ફોર્મ વીક લો ઓફ લાર્જ નંબરના મળતા હોય છે. વીક લો ઓફ લાર્જ નંબરની અંદર ને Chebychev's ઇનઇક્વાલિટીની અંદર સામ્યતા છે. Chebychev's ઇનઇક્વાલિટીમાં જો આપણે રેન્ડમ વેરિયેબલ છે, બર્નોલી રેન્ડમ વેરિયેબલ લઈ લઈએ, એટલે કે XA પ્રોબેબિલિટી ઓફ XA રેન્ડમ વેરિયેબલ એવું લો કે બે જ વેલ્યુ એસ્યુમ કરે, 1 અને 0. 1 એટલે સપોઝ એ એસ્યુમ કરે એની પ્રોબેબિલિટી p કહો, એટલે કે પ્રોબેબિલિટી ઓફ સક્સેસ કહીએ, અને ફેલ્યોર એનું 0થી ઇન્ડિકેટ કરવું, એની પ્રોબેબિલિટી 1 - p કહો. તો આપણે જો Chebychev's ઇનઇક્વાલિટી લગાડશું તો એમાં લિમિટ n ટેન્ડ્સ ટુ ઇન્ફિનિટી તો આપણને પ્રોબેબિલિટી લેસ દેન 1 મળી જશે, એટલે એક્ઝેક્ટ 1 મળી જશે. ટેન્ડ્સ ટુ ઇન્ફિનિટી કરો તો 1 મળી જશે. તો દેટ મીન્સ ફ્રોમ Chebychev's ઇનઇક્વાલિટી વી કેન ઓબ્ટેન વીક લો ઓફ લાર્જ નંબર which is known as the Bernoulli weak law of